Unit 10, Lesson 5. I can solve for segments of tangents and secants. So the prior lesson was about solving for segments of chords. Now we're going to talk about tangents and secants. So here's a tangent right here, touching once, and a secant that would happen to keep going through would touch twice. Let's take a look at this though, a tangent and a radius. Here's your tangent, here's a radius, there's another radius. What is the relationship for these guys? Well, it turns out that a tangent right here, and then we can see the radius there. I'll even color code these guys. Here's my tangent, and here's my radius. Same thing right here, that's another radius. They happen to always be perpendicular to each other at the point of tangency. So tangent is always perpendicular to a radius. And where? It is at the point of tangency, which is right there. That just means the point where they touch. So always 90 degrees, that's the key. And now that can let us use a bunch of relationships which we already know. So if I come over here and zoom in for a second, RP is 13. Let's go find the distance from R to P. This entire distance happens to be 13, and the distance from W to P happens to be 11. Solve for the radius of the circle. So our find is the radius, and in that case, what we're really looking for could be this right here, or that right there, as it's also a radius. Segment from the center of the circle out to the edge. So how can we do this? Well, you can just use Pythagorean theorem really quickly. Okay, a squared plus b squared equals c squared, and get your distance from W to R, which happens to be the radius. So, no problem. Done this a bunch. Go ahead and substitute in. 11 would be one leg. WR happens to be the other leg. And then 13 is the hypotenuse. I'll do this calculation quick. So we get 48. We need to square root both sides to undo the squared. See you later. So I have square root of 48, but the good news is I know that 16 times 3 makes 48. I know how to do the square root of 16. That's a 4. I don't know the square root of 3, so I'm going to leave it underneath, and that happens to be my distance. 4 square root of 3 units is that radius. So the main takeaway, a tangent to a radius, always 90 degrees, allowing you to use Pythagorean theorem to solve for segments. Let's go ahead and look at two other relationships. Again, dealing with tangents and secants today. Here is when we have two tangent segments. If you have two tangent segments, here's a tangent, here's a tangent. Why are they tangents? Because they touch exactly once. That's right. And if the two tangent segments meet at the same exterior point, so notice how this tangent segment and this one meet right here, then they happen to be congruent. So those are the same because they meet at this point here and they're both tangents. So we can go apply this really quickly. We can see the tangents because they touch exactly once and they meet up at the same exterior point. So I can say, sure, you two segments are congruent, which allows me to write 2x minus 3 equals 27. Let's go ahead and use our algebra real quick. And we're good to go. Last relationship, secants. secants touch twice. So secant SD touches here at S and G, and secant HD touches here at H and J. If you have two secants meeting at the same exterior point, then here's the relationship. It's important to write down, and I like to annotate in a specific way. So it looks a little bit like this. You have your exterior segment, okay, which I'm going to highlight here in pink. This is the exterior segment of the secant. It's on the outside of the circle. And if you multiply that times the whole secant, this would be the whole secant. It's equal to the exterior segment of the other secant times its whole thing. So this relationship, again, this exterior bit times the whole thing equals this exterior bit times the whole thing. Where do people go wrong? They use addition a lot instead of multiplication. So let's take this idea and let's walk it over here and look at example 3. Our find is x, and I like to write the relationship down really quickly. I see their secants and they meet out here at an exterior point. So it's the exterior times the whole is equal to the exterior times the whole. I can color code, which sometimes helps me. Here's my exterior part right here. So that's 6 times the whole thing. And this, though, is actually where people go really wrong. So I want you to anticipate, okay, this is the whole thing right here. So what should I put in this spot right there? Okay, what do you think the answer is? 6 plus x, not 6x. 6x is 6 times x, and that's not what we mean. To get the length of the whole secant, you add this segment to this segment. You add them. That's probably the number one place where people go wrong. So the exterior of the other segment is just the 8 times this whole segment here, and the whole segment there would be 8 plus 18. So we really want to watch out for that. It's very easy to mess up. Highlighters help out a lot. And then it's nothing more than algebra. You're going to get, with the distributive property, 36 plus 6x. You could distribute or just go ahead and combine these to get 26. I'll just keep going here. This product is 208. Start to isolate the x by taking 36 from both sides. Let's go ahead and divide both sides by 6. I probably have to go and do long division off to the side. If I do that and come back to my problem, I'm going to look at 28.6 repeating. That's fine. I love that answer right there. It could have been left as a fraction, although I would have reduced it. If I were to round to the nearest tenth, however, I could say that x is approximately equal to 28.7 because this is 6, 6, 6, and it just kind of keeps going, right? That's what the bar means. So if I'm rounding to this place, I round up to the 7. I'm showing that because it's a great question for me to embed in this, hey, round to the nearest tenth. Let's look at the last one. It's actually the exact same approach. Here's a secant, but this is not a secant. This here is a tangent, whereas this is a secant. So we might be saying, well, what's the relationship? And it's actually the same thing. It's the exterior times the whole is equal to the exterior times the whole. And people might say, well, how does that work? I can see the exterior here. I mean, that makes sense. So that's clearly going to be 6. And I can see the whole over here would be 6 plus x. Don't forget, 6 plus x, not 6x. So what's the exterior in the tangent? Well, 10. 10 is definitely the exterior. Well, what's the whole thing over here in the tangent? Well, also 10. And that's kind of the little catch here. They're the same. For a tangent, the exterior and the whole, the same measurement. And then again, nothing more than algebra. Let's distribute. And we'll solve with our algebra skills. What's that going to be? 64 by both sides by 6. I can reduce this, I think, to 32 over 3. Or if you were to go and do long division and then round, I think about 10.7 is what you're looking at here. I think that's the case. So there you go. That's the application of all three relationships here. Make sure to annotate and highlight, and that'll really, really help. Good luck.